All right, thank you for joining us for today's webinar, The Realities of 5G Network Performance. Today's speaker is Michael Thalander, President of Signals Research Group. In today's seminar, Mike will highlight how 5G networks are performing on a global basis, including networks in Europe, Asia, and North America, as well as mid-band and millimeter wave frequencies. In addition to looking at basic performance parameters and the synergies between 5G and LTE, the seminar will examine how 5G delivers a better user experience when today's LTE networks become capacity constrained. The webinar and slides will be available for download after the presentation today. Additionally, there is companion white paper that will be available for download at www.signalsresearch.com. Please be sure to enter any questions that you have throughout the presentation. We will be sure to answer them towards the end. If we don't have time to address all of the questions, Mike will get back to you with an answer following the webinar. With that, I'll give it away to Mike.
Okay, Ben, thank you very much. Just as a little bit of a background, for those folks that don't know who Signals Research Group is, it's a company that I started back in 2004. And literally from day one, a key focus of our organization has been on doing performance analysis, anything from chipsets to devices to the radio access network. Started back in the day looking at 3G, WiMAX, fast forward to LTE, 4G. And then starting in January of 2018, started looking at 5G. And at the time, it was really looking at Verizon's fixed wireless deployment, their trial network in Houston, Texas. But since then, we've had the opportunity to really travel around the world looking at the performance of 5G networks. In June of this year, Qualcomm reached out to us and asked us to kind of assemble all of our material together that we've collected over the last year and a half to do a white paper and a presentation, for you today. And so I guess the point there is that most of this material is stuff that we've collected and analyzed on our own without any vendor involvement. There's a couple minor exceptions. We did some testing in Europe as part of this study, but everything else was really done prior to this engagement taking place. So in terms of key highlights, we found that already 5G is providing meaningful capacity gains relative to LTE on a global basis. Looking at millimeter waves, it actually turns out they're far more resilient than generally perceived. In fact, that also goes indoors. We had the opportunity just a few weeks ago to go out and do some testing at US Bank Stadium in downtown Minneapolis, and I'll be covering that today. The capacity gains that we're seeing in the 5G networks also have a meaningful impact on the user experience in terms of application downloads and video streaming. And that's especially true when LTE networks become capacity constrained. And then finally, and this I think is fairly interesting, 5G is actually, or can be, more energy efficient than LTE and also deliver a full day's worth of battery life under most scenarios. So we'll start off by looking at 5G performance on a global basis, and we'll start in South Korea. So we were in Seoul, South Korea back in June of this year, and we were actually there for about 4 days, tested over a period of 3 nights and a couple of afternoons. During that time, we transferred more than 2 terabytes of data. Now, when we do our data collection, we're actually using a combination of taking information out of the chipset and also using a scanner and also using a high bandwidth server. The parameters that we collect are literally hundreds, and we're collecting them up to 1,000 times per second. So it's really a rich set of data. What I'd like to do today is just summarize some of those KPIs, and obviously data speeds and throughput mean the most to most listeners, so we'll try and focus on that aspect, as well as talk about some more important parameters that we've analyzed. So this is a walk test that we did in the late afternoon in the Gangnam area. This is near the COAX buildings that are located in the Gangnam area. This was a 4.6 kilometer walk, and during this walk, we actually transferred 192.8 gigabytes of data. What I'm showing down in the bottom left-hand corner is the actual walk test. And then on the right-hand figure, the red, that shows where 5G was available. And you'll notice if you look at the two figures, there are a few places where 5G was not available. One of those reasons is that when we do our testing, we're using a high bandwidth server pushing data for up to several minutes at a time. But then obviously the test scenario ends and the test starts up again. And during that time frame, there's obviously no data being sent. And so we'll get 0 megabits per second and no 5G connectivity. There's another important reason why there always wasn't 5G connectivity, and I'll discuss that on a later slide. So looking at the top figure here, this is a plot of the throughput. You see the x-axis is time, and then along the y-axis, that's the data speeds. So this is walking in the Gondom area holding two phones. One is the LG V50 configured to support 5G. The other is an LG V50 that was locked to LTE only. And we're plotting here the data speeds. You see the blue line, that is the 5G physical layer data speeds. Now on top of that, you will see the orangish line or the yellow line, that is the LTE throughput that phone is also receiving. I think this kind of brings out a very important aspect of today's networks. When you're looking at your phone and you're actually using it in a 5G network, most of the time the phone is also connected to LTE and receiving data throughput over the LTE radio bearer. Now what I haven't plotted here is really the summation of the two. That is what you would see if you're doing, say, for example, a speed test and you get a certain data speed. What you're really looking at is a combination of both the 5G data speeds as well as the LTE data speeds. Now the green line that we've plotted here is the LTE phone, and that is obviously just the LTE data speeds that phone is receiving. But the net is that having two phones side by side over a 5-kilometer walk, we see that the 5G enabled phone has substantially higher throughput. This next slide attempts to summarize the data speeds we saw on the previous slide. And this is just a summary over the entire test. So I'd like to draw your attention to two bars that are of most importance. You see the third bar from the right, the one labeled total throughput 5G phone. That phone, the median throughput was 260 megabits per second. Now that compares with the second bar from the right-hand side, or the 4G throughput at 100 megabits per second. So looking at the throughput comparison, we see that the 5G smartphone was actually 2.6 times faster than the LTE smartphone. Now let's take a look at the other bars. So starting on the left, that is the 5G smartphone, and that's the 5G data speed observed by the 5G phone. The second bar is the LTE component. Now, an observant listener will notice that the summation of 197 plus 63 does not equal 260. And the reason behind that is that the 5G phone wasn't always connected to 5G or using 5G. Likewise, the 5G phone wasn't always using LTE. And so that's why the summation of the two does not equal 260. Now, the other important thing to do is when you're looking at networks is to factor in network loading. And we do that through the process known as resource block normalization. In essence, we're taking into consideration other users in the network. So let me give you an example here. So let's imagine you have an LTE radio channel that's 20 megahertz wide. That supports 100 resource blocks or 100 network resources. Now let's assume your smartphone was getting 50 of those 100 resource blocks. That basically means you're getting half of the network resources, and half of the network resources are going to other smartphones in the network. In effect then, with resource block normalization, we're calculating what the estimated data speed would be if the smartphone would have received all of the resource blocks. And when we do that, we see that between the combination of the 5G component and the LTE component, the 5G-enabled smartphone had a median data speed of 512 megabits per second. Now we compare that to the LTE phone, again, only using the LTE radio channels. Its resource block, or its RV normalized data speeds were only 268 megabits per second. I should also note that since we did this testing in June, obviously this may not reflect the current capabilities of the network. I was at Qualcomm's 5G Summit last week, and I heard SK Telecom talk about how they've added a lot more 5G cells into their network. So I think the point here is that the results we're seeing are based upon the capabilities of the network back in June and may not be reflective of the network today. Now let's turn to Europe and look at EE's network in central London. What I've plotted here is the ENDC throughput, or basically the summation of the 5G data speed and the LTE data speeds. Now in this case, EE has 5 component carriers for LTE, a total bandwidth of 95 megahertz of spectrum. And then on top of that, they have the 5G network, in this case, deployed at 3.5 gigahertz, where they have 40 megahertz of bandwidth. Now, this is a test that I did in the morning hours. I was actually walking to Victoria Station, where I was doing a lot of the user experience tests, and then obviously walking around afterwards. So during this nearly 7-kilometer walk, I transferred 135 gigabytes of data. And this is only using the 5G phone. In this particular test, I did not have an LTE phone running in parallel. So let's take a look at the throughput. And here what we've plotted is the distribution of the data speeds for the 5G phone. The blue line is the LTE component. The green line is the 5G component. And then the gray line is really the summation of the two, or what the end user would observe. And so what we see is that in total, the median data speeds was just north of 220 megabits per second. The other thing to note is if you look at the x-axis, that is 0 megabits per second, you will see that nearly 20% of the time the phone was not receiving any bandwidth or any data on either the 5G or the LTE network. And again, that stems back to our testing methodology, where there are periods of time, when the phone is not receiving data because the application is reset. There's another important reason here, and this refers to the way ENDC works today. So quite often, obviously, you will have data speeds coming over both the LTE radio channel as well as the 5G radio channel, but it doesn't happen all the time. And I think that's one area of improvement that we can see in the future here, whereby the operators and the vendors have more efficient use of their LTE networks. So they're always scheduling data on both the 5G network as well as the LTE network. And when they're doing so, they're actually fully optimizing or fully utilizing the capabilities of the LTE network. And when they do that, I think we'll see substantially higher data speeds than we see today. The other factor that I'm not showing in today's presentation is the uplink. And obviously, although the downlink carries most of the data in today's networks, the uplink component is also very important. And what I would say here is that by and large, the LTE networks actually deliver higher data speeds. And this is kind of a near-term effect, and there are a couple of reasons behind that. So first of all, this is, in today's 5G networks, it is TDD based. So you're sending and you're both transmitting and receiving data in the same radio channel. But that radio channel is disproportionately configured to support the downlink versus the uplink. And because of that, there's less time available for uplink transmissions. That tends to give you higher data speeds in the downlink, with the adverse effect being, lower data speeds in the uplink. On top of that, a lot of operators today are using carrier aggregation in the uplink on their LTE networks. So the fact that you may have, say, 40 megahertz of spectrum in FDD transmitting in the uplink, that's a tremendous advantage versus using TDD for the downlink and uplink transmissions. But keep in mind, this will change over time, obviously, as operators start deploying 5G in their lower spectrum where they have FDD bands. On top of that, 5G also supports carrier aggregation in the uplink. It's just that we haven't seen that deployed at this time, but that should be coming in the coming years. So now we'll turn to 5G millimeter wave and take a look at some of the performance in today's networks in the US with both Verizon as well as T-Mobile. Now, when we do our analysis, you know, throughput is interesting, but I would argue it's perhaps not the best metric when it comes to looking at the performance of the network. So what we've plotted here, this is downtown Minneapolis. This is data that we collected with the Motorola Moto Z3 smartphone with the 5G module. And what we've plotted here is the signal quality, or the B-SINAR. And if you're looking at this chart here, basically, you know, everything is collected by the Motorola phone. Obviously, the magenta, having a higher SINAR is better than a lower SINAR. To put things into perspective, kind of the average SINAR in this collection of data tests was around 12 dB. Putting that into a calculated user data speed, it's around 500 megabits per second. The other interesting thing to point out here, and it's not obvious, although we did a lot of this data collection while walking, we also collected a lot of data while driving around the city in a Ford F-150 pickup. And so I would argue that 5G millimeter wave is not just about being a pedestrian on the street. It's actually a very usable technology when riding around in a vehicle, be it a car or a bus. So this is an interesting slide. What we've shown here is one area in downtown Minneapolis, and I'd like to draw your attention to a few things. First of all, you will see the series of colored circles starting from the top, going vertically down towards the bottom. That's Nicollet Mall. Nicollet Mall is very important to Minneapolis. I was here on April 6th of this year watching the NCAA Final Four games. I was here also about a year and a half ago when Minneapolis hosted the Super Bowl. Everybody hangs out on this street. It's kind of the place to go when there's something happening in the city. So what we're showing here, first of all, let's take a look at the colored arrows. Each of those colored arrows represents a 5G radio. The direction of the radio, or the direction of the arrow, is the direction that the radio is facing. You see the colored circles, the green, the blue, the magenta, etc. Those circles indicate the cell site that the Motorola phone was attached to at that point in time. This is a test that started at the top of the page, basically walking down Nicollet Mall towards the green arrow, turning around and walking back. A couple things to note here. First of all, you will notice towards where I've highlighted the yellow circle, you will see the blue and the magenta. That's actually coming from the cell site about a block and a half to the left on 11th Avenue. Now the key thing here is that you will see the magenta arrow. It's actually facing in nearly the opposite direction. Yet the phone was attached to that cell site for about 10 seconds on the way back. Now, I would argue there's no way that millimeter wave signals come out the back of a 5G radio. So the only way that signal reached that phone was through reflections. And we've highlighted that on the picture here. This is St. Thomas University. There's both a skyway that crosses the 11th Avenue as well as a building there. And so our belief is that that signal actually reflected off of those buildings, came all the way back nearly 2 blocks to our mobile phone. To me, that's very impressive. A couple other things to point out. First of all, there's actually 3 5G cell sites that are actually in this area that are not shown on the figure. Each of these cell sites actually has 2 radios. And so I've just highlighted those cell sites are those 5G radios that are pertinent to this conversation. The other thing to highlight, and we'll come back to this in a little bit, are the black circles. Those black circles indicate periods where the 5G phone was not connected to the 5G radio bearer, and we'll discuss why that was the case in a little bit. So here's a picture of that cell site that was actually providing connectivity back to Nicollet Mall and the Motorola phone. We see here PCI 49 and PCI 50. So PCI 49, that's the one that's actually facing towards Nicollet Mall. It would kind of make sense that you could connect to that radio because it's only about a block and a half away and is facing in the correct direction. PCI 50 is actually pointed 135 degrees in the opposite direction. And this really, it's a little bit hard to see in this picture here, but trust me when I say that when you're looking at that radio and standing on 11th Avenue, the only thing you see is the backside of the radio. So again, I think this furthers the proof that there's actually millimeter wave reflections that were connecting back to the smartphone on Nicollet Mall. So this is a time series plot of the data speeds that we observed. And again, this is testing that we did back in April of this year. So this is a time series plot starting on the left-hand side. That's when we're on the intersection of 11th and Nicollet Mall. And then obviously we walk towards PCI 229 on 12th Avenue. And then at the end of the plot, around 300 seconds, that's when we've actually gone full circle and then ended back up where we started. So the green here is the 5G throughput that the Motorola phone observed. You see instances there, say for example, starting at around 26 seconds. For some reason, and we'll explain why in a little bit, the 5G phone actually lost the 5G signal. It fell back to LTE. Now those LTE data speeds may look low, but it's really because it's relative to the 5G data speeds. On average, they're around 200 megabits per second in many cases. So now let's take a look at around 275 seconds. What I've highlighted here is the throughput being observed from the radio, the 5G radio that was pointed in the opposite direction from where I was standing. And we see that the data speeds were actually around 200 megabits per second. So now let's take a look at why the 5G phone was losing the 5G connectivity, even though we were literally standing right in front of the 5G radio. So what we've plotted here is a couple of things. Along the x-axis is time, and again, starting at the left-hand side, that's where we're at the intersection. We walk a block and turn around and walk back, and so around 325 seconds, we're basically back at where we started at 0 seconds. We've plotted several things here. You'll see the squiggly lines, that represents the signal strength. And so we see the 5G signal strength there. So what happens? At around 25 seconds into the test, we see a very strong signal. Now I should point, actually, the secondary y-axis is the signal strength. So at that point, the signal is very strong, and then all of a sudden it goes away. And then around 75 seconds, the 5G connection comes back, and again, the signal is very strong. So it wasn't a weak signal that caused the 5G phone to lose 5G connectivity. So what's happening? So let's take a look at the blue line. So the horizontal blue lines reflect the LTE cell site that the 5G phone was connected to. Now keep in mind with 5G today, there's that feature called ENDC, or with the NSA network architecture, where you actually need an LTE anchor carrier to support the 5G connection. So what's happening here is that every time we lose the 5G signal, there's actually a change in the LTE cell site. And we see that at around 25 seconds, where the horizontal blue line shifts and it goes up much higher. Again, when the connection resumes, again, the 4G cell site again changes. So what's interesting, over about a 1.5 block walk, our smartphone was connected to 4 different 5G cell sites, and it was also connected to 5 different LTE cell sites. And the problem here is really one of optimization. So when operators are optimizing their networks, they try to map together those LTE cell sites and 5G cell sites where they expect there to be kind of a relationship. What can happen for a number of reasons is that there may be an LTE cell site that's providing coverage into an area, but that LTE cell site is not mapped to the 5G cell site. And so when that happens, obviously the LTE cell site doesn't know there's a 5G cell site out there, and so you stop receiving 5G connectivity. So again, if a casual observer out there, if they're doing, say, a speed measurement application and they're doing a speed test, they don't see the 5G radio bearer, the conclusion may be, well, millimeter wave doesn't work. I'm not seeing a signal. What's going on here? The reality is that it has nothing to do with the 5G signal itself. Instead, it's just very basic optimization that can take place to really improve the reliability and connectivity of 5G. Here's another example from downtown Minneapolis. So what I've highlighted here is PCI 99, and we see that in the left-hand figure. I've highlighted the other radio that's actually mounted to that cell site. And then you see way in the distance there with the red arrow, that's another 5G cell site pointed back towards us. So the interesting thing here is PCI 99, it's not pointed down the street. It's actually pointed 45 degrees into a building, pointed into an office window. This is a 5-story building, and it's basically at the 3rd level pointing into it. And we saw that, and it really didn't make any sense, and I really can't explain it today why that radio is pointed into the building. But it actually results in some very interesting results. So now on the right-hand figure here, this is a geoplot. You see the yellow arrow. That is indicating the location and the direction that the PCI 99 5G radio is pointed. What we've plotted here, again, this is collected with the Motorola smartphone. This is the signal strength that was measured. And in this case, we tried to keep it fairly simple. Basically, green is good, yellow is marginal, and red is not so good. In layman's terms, green is RSRP that is better than neg 105. Yellow is between neg 105 and neg 110. And then red is below neg 110. All of these are signal strengths that are definitely feasible for providing a 5G connection, but red is obviously a bit tenuous, not guaranteed to give you a high data speed. But the interesting point, again, is that if you look at the yellow and the red that is basically horizontal on the page, that is non-line of sight to that yellow arrow. There is no way in heck that that signal is going through a building and coming out on that adjacent street. So again, the only way I would argue that that signal is reaching the phone is through, I would believe in this case, actually multiple reflections. And again, delivering not necessarily a great user experience, but again, demonstrating that millimeter wave is pretty resilient and it does not need line of sight conditions in order to provide a connection. Switching gears, this is T-Mobile's network. This is in New York City. We had the chance to go testing there in early August. I'd like to draw your attention, first of all, to the right-hand figure. What I've highlighted here are two 5G radios. You see the 2 yellow rectangles there highlighting the 5G radio. This is about 5 stories up on an office building. T-Mobile, at least in New York City, their deployment philosophy is different than what I've seen with Verizon in Chicago as well as in Minneapolis. They tend to locate their 5G radio assets on top of buildings, again, co-located with their LTE radio assets. Now let's turn to the left-hand figure. What we've plotted here is the location of the 5G cell site with the 2 5G radios. you'll see a bunch of colored circles here. What these circles represent are the beam indices. And so we see the autumn colors, if you will. That's the browns and the yellows and the red. Those are the beam indices for the 5G radio that we see on the right-hand side. And then the purples and the blues, those are the beam indices for the 5G radio that we see highlighted, again, in the right-hand figure with the left radio there. And so the point here is a couple of things. First of all, from a single location, your 5G radio assets using millimeter wave can actually cover in multiple directions. I think the other interesting thing is that this actually exemplifies the capabilities of millimeter wave and the fact that you're actually using multiple beam indices within each 5G radio. You can kind of think of that as directional energy. You know, it's more like a laser focus than it is a light bulb. And that's really necessary to maintain good propagation with 5G millimeter wave. It's also a feature that exists with sub-6 gigahertz 5G deployments. To this day, however, I have not seen it being used. So that's definitely another area of opportunity for improvement, that once you start using individual beam indices, you can definitely improve both your coverage and your capacity. And when it comes to sub-6 gigahertz 5G deployments, it also allows you the ability to support multi-user MIMO. Again, really increasing the capacity of your network. There's a lot of talk about, well, how does the phone get impacted by body blockage, by how I hold the hand? Well, this is a test that we did to really capture the impact of holding the phone in various configurations. And I should mention, in the white paper that Ben alluded to, we also look at the impact of holding the phone in portrait versus landscape. So we've plotted here a few things. So this is testing done in downtown Minneapolis. Is with the Galaxy S10 smartphone. We see the dashed lines, that represents the signal strength, and that's plotted along the secondary y-axis. Here, blue is the LTE signal strength, and green, the dashed green line, is the 5G signal strength. We've also plotted the data speeds, and here the solid green line is the 5G throughput, and the solid blue line is the LTE throughput. So right around 25 seconds or so, I started gripping the back of the phone. And when I did that, we started seeing an impact in both the signal strength as well as the signal quality and the data speeds for the 5G phone. But I wasn't killing the connection. So then around, say, 35 seconds or so, I gripped the phone as hard as I can with both hands, squeezing as tightly as I can. And ultimately, when I did that, I was able to cause the 5G phone to lose its connection. But you'll notice I also impacted the LTE signal. So yes, definitely, you can have an impact on your 5G signal, but it takes a lot of effort to do. And when you do that, it also has an impact on your 4G signal. So again, it is definitely true that millimeter wave is not completely impervious to everything. But I would argue that it takes a lot of effort to really impact a 5G signal on your phone based upon how people would normally hold their phone. Now we're going to turn to indoor deployments to take a look at what Verizon Wireless is doing when they deploy 5G at some of the NFL cities around the country. And I believe they've announced they've deployed at 13 NFL cities. I reached out to them in September and I said, hey, is this for real? And they said, yes, it is. Come and check it out. And so we spent the day at US Bank Stadium in downtown Minneapolis, home of the Minnesota Vikings. So on the left-hand side, this is a picture I took of a 5G cell site. You see the 5G radios at the top of the picture. This was taken back in April 2019, just a couple of weeks prior to Verizon launching their 5G service. And then on the right-hand side, this is the same, basically inside US Bank Stadium. What I've highlighted here are two 5G radios that are mounted in a catwalk, which runs right down the middle of the field. In total, Verizon has 13 5G radios in US Bank Stadium. 12 of them are mounted in the catwalks, providing coverage to the stadium. There's actually a 13th that is mounted at the Verizon gate, where they actually will be selling phones and provisioning phones during the football games. If I was to zoom out this picture a little bit, you'd actually see some more 5G radios. And it's my understanding those are most likely AT&T, who has also deployed 5G in US Bank Stadium, but at this point, it is not commercial. So here's an inside of US Bank Stadium. This is a picture that we took. That's me sitting down there at the left-hand side. There's a picture of my view in the top left. And then on the right-hand side are my data speeds. We did 3 tests from sitting in this seat. And this is really to focus on the impact of the data protocol being used to send the data. So we used the same server for all 3 tests. In the first test, we established 12 parallel HTTP data threads. And when we did that, we had an average data speed very close to 2 gigabits per second. We then reduced the number of parallel threads to 2 and to 6. And when we did that, despite not changing locations, despite using the same server, the data throughput dropped considerably. With 2 parallel threads, the data speed was only 155 megabits per second. And with 6 parallel threads, it was just north of 300 megabits per second. And the reason we did this testing is twofold. First of all, a lot of people like to go out and do their testing of networks, and they'll collect a lot of data. They have a lot of results, but not really a lot of information. And one of the problems with the results they get is that typically these data servers used for testing purposes are sitting right next to the operator's gateway. On top of that, they're using multiple threads to send the data. Now, there's nothing wrong with that at all. Obviously, we do something very similar. The challenge is that not all applications and content uses multiple threads. And so you may get a very good experience doing a speed test, and then you turn around and try to download something from a host server somewhere. If they're not using a lot of parallel data threads, your throughput can be considerably lower than what you're measuring and doing your speed test. And again, this is not a negative reflection on the 5G network at all. It's just the reality that, today's 5G networks are actually becoming better than the internet themselves. And so it's really important to look at, what protocol you're using and where is your server located. And I guess I would argue there's a lot that the various content providers can do to optimize their servers to make sure that they don't become the bottleneck in today's 5G networks. So how was the experience at US Bank Stadium? We collected a ton of data. I've got a couple of slides to share with you today. This is a test looking at signal strength. And you see here, this is really the top row of US Bank Stadium. It's actually, if you're scared of heights, it's a little bit tenuous there walking. But in any event, you'll see really outstanding signal strength throughout the entire walk. And that's really to be expected because, in fact, the 5G radios are right in front of you. And so this is actually not necessarily a challenging place to provide 5G coverage. Instead, it's a very logical place, given the fact you have around 66,000 people watching a football game. There's obviously a lot of need for capacity in the network. It's actually, in a way, I would argue, very easy to have 5G coverage in a building like this. Now let's turn and look at data speeds. And I think this is actually quite interesting. It's not obvious in this figure, but what we see here is a walk test. The walk test actually occurred behind the stadium seating area. So this is where people go out to buy their brats and their beers, use the bathroom, etc. In most cases, you can't even see the 5G radio. The only way that signal is getting to you is that it's leaking in between the seats. So despite that fact, we see that typically the data speeds are well north of 1 gigabit per second. And again, we see those very periodic periods where it's black. Most likely those are cases where the data application test had ended and it's recycling, so there was no data being pushed to the phone, hence the throughput is low. So now let's turn and look at how these capacity gains that we're seeing in today's 5G networks actually impact the user experience. And I should mention there's a lot more information in the white paper that's coming out or that's available today. I'm just going to try and highlight a few of those today. Let's take a look at YouTube. So this is testing that we did in Victoria Station in central London. This was during rush hour traffic. And the goal here was to have two phones side by side playing the same YouTube video, streaming it at HD 1080p. So we see here a couple of things. First of all, in the left-hand figure here, we see the green and the blue. The green is the 5G throughput going to the 5G phone. The blue is for the LTE phone, representing its throughput. So for the 5G phone, since the goal was playing it at 1080p, it had no problem doing so. And we see the black line across the top indicating that the 5G phone had 1080p throughout. Now the LTE phone is somewhat different. It actually started off at 480p. We had set the YouTube video to play 1080p, but the application sensed that it could not handle 1080p, and so it started playing the video at 480p, and even then, it realized that it couldn't handle, that kind of video resolution. It actually dropped to 360p at around 15 seconds into the test. So in this case, both videos played fine. The benefit, however, for the 5G user was that they had a better viewing experience because it was a higher resolution video. And again, in the white paper, we did lots of other tests looking at kind of the basics of Netflix and downloading Angry Birds and all the things that people like to do. And those results also show a very similar trend in that, the 5G connectivity, obviously you see faster download times, definitely benefiting the user experience. And then the last thing here, it's somewhat not as important, but we see the impact on how long it took for the video to start. And again, these times are fairly short, but what we see here is that the LTE smartphone, it actually took a 2.4 times longer to start playing the video than the 5G smartphone. And again, that was starting at 480p versus 1080p with the 5G smartphone. Now for the final section, we're going to turn and look at energy efficiency. So before kind of discussing this slide, let me explain a little bit about what we did. So this was testing that we did in downtown Minneapolis, actually around Minneapolis. We went out and characterized the network, both 5G and LTE, identifying things like signal strength, signal quality, the number of concurrent carriers if it was LTE. We then did a long sustained throughput test, and during that test we measured the application layer throughput, and we also measured the current consumption. To put things in perspective, kind of the data speeds we see here for the LTE network, they range from around 70 megabits per second to around 200 megabits per second, and then for 5G, anywhere from 400 to 800 megabits per second. What we're plotting here is the relative energy efficiency compared to 5G with a very good signal connection. And what we see here is that if you look at things in terms of kind of the bits per hertz, or not bits per hertz, but actually the energy consumption as a function of the data speeds, it actually turns out that LTE is definitely less efficient than the 5G network. That's not to say that 5G has lower current consumption, and in fact, 5G definitely has much higher current consumption. The benefit, however, the trade-off is that it also has much higher throughput. So because of that, if you look at energy efficiency or how much energy it takes to transfer a certain amount of information, it turns out that with very high bandwidth applications, or anytime you're trying to push as much data as possible, 5G is actually more energy efficient. Now, we also look at 5G compared to LTE, where we intentionally throttled the data speed. We looked at 5 megabits per second and 30 megabits per second. 5 megabits per second is roughly equivalent to a FaceTime video chat, and 30 megabits per second is roughly equivalent to the amount of capacity needed to watch a 4K video. And when we did that, it actually turns out LTE is more energy efficient, and the numbers are somewhat comparable to what we see here, just in the opposite direction. And the reason behind that is, in this case, your 5G phone is using 400 megahertz of 5G spectrum plus the LTE, but in doing that, it's only sending a very small amount of data. And because of that, its current consumption is higher, but it's not benefiting from the 5G network and its ability to actually receive more data at a faster speed. So let's take that information and actually calculate what it means to the user experience. What we've plotted here are 3 scenarios, and what it is showing is the amount of data that you can download on a battery charge. And this is basically the Samsung Galaxy S10 has a 4,500 milliamp hour battery. Its minimum threshold is 4,400 milliamp hours, so we use that as the basis for the study. So looking at the current consumption versus the relative data speeds that we observed in these various scenarios, what we see is that, again, based upon the backlight, over a 5G connection, the 5G smartphone can actually download substantially more data than the LTE smartphone configured to an LTE network. With no backlight on, for example, you can download nearly 330 gigabytes of data before your battery dies. That compares to only around 170 gigabytes with a no backlight on the LTE connection. The other point I want to mention here too is that we actually saw the best network performance on LTE in Verizon's LTE network in downtown Minneapolis, where they've also deployed 5G. And I think the reason behind that is the use of small cells. And even though they only had 2 carrier aggregation in downtown Minneapolis, the results were very impressive, around 200 megabits per second on average, again, really due to small cells. And that's something to think about, is that people talk about, well, the impact of deploying 5G millimeter wave. And yes, there's a cost there involved, but there's also a benefit in terms of what it does to your LTE network, and we're seeing that in today's results. Obviously, nobody goes out and downloads 200 gigabytes of data all at once. That's not how you use your phone during the day. So this chart here looks at, okay, how would a person actually go out and use their phone, and what does that say for the amount of battery they would have throughout the day? So we made several key assumptions. In this particular scenario, we assumed that the person downloaded 1.5 gigabytes of data throughout the day. Of that, 80% was only sent at 5 megabits per second, 10% at 30 megabits per second, and then 10% at the max speed. So here we've actually severely penalized the 5G phone because we're not allowing it to take the full benefits of the 5G radio bearer. We assumed 50% display brightness. We assumed the person was making 3 hours of multi-calls, 4 hours of doing other things with the backlight turned on. So, for example, they may be playing a game on their phone that's not necessarily connected to the network, but the backlight is on. They could be taking pictures. They could be looking at pictures. Again, that is something that takes energy. Once we calculated the energy budget for all of those activities, we looked at the remaining delta in terms of how many milliamp hours were left. Using that information, we then calculated how much idle time the phone would have. So now what we've plotted here are 4 different scenarios. On the left-hand side, we assume that this 5G phone was entirely in an LTE network. And then at the other side, on the far right-hand side, we assume the exact opposite. The 5G phone is always connected and in a 5G network. So what we see is that obviously when you're in the LTE network, your battery life is the longest. But even if your phone is in a 5G network throughout the entire day, despite the fact that you're not taking any benefits or getting any benefit from the 5G faster connection, we still see that the battery life can definitely last, well more than 13, 14 hours, which I think is quite good and definitely well within the normal workday. The other point I want to make here is that one of the reasons the idle time drops more considerably with the 5G connection and then the 5G network versus LTE is that we've noticed that in a 5G network, even though the phone is not connected to the 5G radio bearer, its idle current consumption tends to be higher. And I think this is because in today's phones, you have a 2-chip scenario, and every once in a while, the phone can detect that 5G radio bearer. And I think it causes the phone to spin up kind of the 5G modem. So this is probably more a near-term thing than anything else. I think over time, as we start going to a single chip solution, we'll see greater efficiencies and improvements in energy consumption, even when the 5G phone is only in an LTE network, but sensing the 5G radio bearer. I'd like to give a special thanks to everybody that's worked with Signals Research Group over the years in testing the 5G networks. I've worked with Spirent really since 2004, doing lots of testing. We use their Umetrics data platform, both for video testing as well as to push data to the phone, be it at 5 megabits per second or at 2 gigabits per second. They've also collaborated with Wireless Metrics, integrating in both their LMH and LMA solutions to really allow you to look at both physical layer and application layer throughput at the same time. We've also found with 5G testing, it's really important not just to capture chipset information, but also using scanners as well. And I didn't really showcase a lot of scanner results today, but we've worked with both PCTEL and some recent testing in Chicago and Minneapolis on Verizon, as well as Roding and Schwartz going back to the very early days of testing in Verizon's network to really look at performance from a scanner perspective. And then finally, AccuVer to capture the chipset information. I've been working with them since really the first days of LTE when we tested the first LTE networks. So in terms of final thoughts, I think 5G is definitely improved. I think there's, finally support now for both 5G throughput and LTE throughput at the same time. When the first 5G networks launched with millimeter wave, you didn't have handovers between 5G cell sites or between 5G beam indices within a cell site. That works today. I think that's definitely a step in the right direction. It's also very clear that consumers and mobile operators are already benefiting from the capacity layer. We saw that in terms of the improvements in the user experience. And then finally, although I think we've definitely made good progress in the last 6 months, there's definitely opportunities for improvement. I highlighted several of these in the presentation already, but just to summarize, definitely better utilization of ENDC, making sure that you're fully scheduling both the 5G and the LTE radio bearers concurrently. 5G and millimeter wave, today's networks by and large are limited to no more than 400 megahertz of spectrum. Operators have up to 800 megahertz in some markets. So as they start to add more channel bandwidth, we'll see an improvement in data speeds. It's a big thing now. The press is talking about it, putting in 5G into sub 6 gigahertz. That to do that, you need both dynamic spectrum sharing and support in the chipset. And that is coming later this year into early next year. And then finally, leveraging NR carrier aggregation. And when you do that, you can essentially improve your higher frequency band as well by shifting a lot of the uplink data transmissions to the lower frequency 5G radio bearer. And so with that, in the final minutes or so, we'll definitely take questions. So Ben, I'll turn it back over to you for any questions we may have.
Great, and thank you so much for that presentation. Wonderful information. So we do have time for a few questions. I will start with the question from the audience. What spectrum is used for 5G in those Korea tests?
Yeah, that was 3.5.
Okay. Is the download
3.5 gigahertz, I'm sorry, and they had 100 megahertz of spectrum there.
Super. And is the download speed testing using local FTP or public FTP server with multiple download sessions?
So in most of the testing, we use the Umetrics data platform from Spirent. In Korea, there was a platform actually set up in Korea. In the testing we did in Europe, we actually used basic user applications, Google Drive, Google Play, Netflix, all of them running kind of concurrently to push as much data as possible. But we tend to use the Umetrics platform as much as possible when it's available.
And do you have data for observed latency?
It's by and large comparable to LTE today. I mean, I don't see a big improvement in latency today. Once we start going to the standalone architecture with the 5G core network, that's where we really start to see the improvements. So it's comparable to LTE.
And why BSINR? Why are those measurements not continuous?
So, sorry, say that again.
So why are BSINR measurements not continuous?
I'm not sure which figure that was alluding to, so I'm not quite sure how to answer it.
Okay. How well did the phone do when it was handing off between each cell site?
I'm sorry, you broke up. Can you repeat that again, please?
Yeah. How well did the phone do when you were handing off between each cell site?
So starting off in the very early days, as I mentioned, there wasn't connectivity between 5G cell sites, and so you would very briefly go down to LTE, and the same was true even within a 5G cell site as you're going in between beam indices. Today, that problem no longer exists, and you can definitely do smooth handoffs in between 5G cell sites. The same thing is true, looking at sub-6 gigahertz, where it's fairly continuous. There's really not any latency or any problems in handing off between 5G cell sites.
Great. And is the reflective wave from the building glass similar to the street canyon effect? You need to repeat that.
Try that again. Yeah, I mean, it's I'm going to call it a canyon effect as I would so much as just basic reflections. And we actually saw that more so with doing our fixed wireless testing. And that's one thing I'd like to mention here is that kind of one of the challenges where we don't see even more reflections is that we're dealing with an uplink constraint on the smartphones. And so when you have a fixed wireless scenario, you have a much higher transmit power coming out of the CPE. And so you actually see far more reflections in a lot of interesting scenarios because the uplink problem doesn't exist to the same degree. I think that's an advantage of DSS and putting 5G in a lower frequency band. If you can move those 5G control channel information in the uplink from millimeter wave to a lower frequency band, I think we'll see even more interesting performance in the downlink in these millimeter wave frequencies.
Okay, great. I think we have time for one more question. So let's see. I'm just curious, what happens to throughput when there are 56,000 people accessing the 5G network?
Yeah, they'll definitely go down. I mean, I'm not going to argue with that. I guess my point, and we tested it obviously in an empty stadium, it'd be impossible to walk around if there were 60,000 people in the stadium. But I think nobody questions the fact that 5G has a lot of capacity. With millimeter wave, the concern is really one of coverage. And so we wanted to demonstrate not so much the data speeds themselves as it was more so the coverage, And so, yes, data speeds will obviously go down just as they do with LTE, but the starting point is pretty high. And then obviously, operators in some markets can add more spectrum in their millimeter wave frequency bands as well to the extent that they have it.
Great. Well, I think that's all the time we have for today. But as Mike and I mentioned earlier, of all these questions that were unanswered, Mike will be happy to follow up with you afterwards. So thank you, Mike, and thank you to our audience again for staying tuned to our presentation today.